What's up, you guys? It's Andrew from Seal. Quick wrist check. All titanium Mark 1 Omnidiver, case number 0. Pretty much the only watch I wear every day, other than the PVD coated version that I have. That's TE256, I think, is the case number on that one. Anyway, quick intro on this video. So we have two distinctly different types of content on the channel. The lifestyle stuff is all about things our customers are doing and things we're doing outside of the office, like on the weekends or in the evenings. Desert racing, supercars, shooting, diving, search and rescue. Pretty much anything that's like super fun and awesome, we'll go make a video about. This video is definitely a watchmaking video. It's not a how-to per se. It is a deeper look inside of our design philosophy and the process that we use for engineering and manufacturing the display elements of Seal watches. We're gonna jump into this one just as I realized the date window was in the wrong position for the D42. So at the same time I'm doing all this parametric modeling, I also have the rendering open on the other screen. So by default, I put the date window right where we use it for the Mark 1 Omnidiver. But the problem is for D42, because I've changed where the hour indices are, they're actually on a smaller diameter hole pattern. So instead of being out here, it puts the date window basically right over the 2 o'clock index. So I want to get a measurement to basically clock this feature. We're going to clock it down this way just a little bit. So we're over here at the optical comparator. I have a movement already set up in the system. I need to get a measurement from the center to this number 13 because that's the position on the dial where we're going to put the date window. So to get this first measurement, we're just going to come over here. And I'm basically going to go right to where I think the center of a circle that would capture that 13 would be. And then we're going to pull this other dimension here like that. So right about there would put the window where I want it to be. So those are my coordinates. So taking the measurements that we just got off of the comparator, I created a solid in the center here, the blue cylinder that's 101.5 thousandths in diameter. That's the window size that we use. So now on the rendering, I already moved the date window position. So it's now here, and that's a good spot for us. Before, it was cutting this index right in half, which obviously that doesn't work, especially if we're going to use an applied stainless steel index like we sometimes do. And the date window is optional on D42. It's also optional on the Mark 1 Omnidiver as well. This is the concept rendering for the D42, and there are a couple things we're looking for aside from just aesthetics. So for example, one of the things we're always looking at is the function of each hand and how it interacts with the other dial elements. So for example, on this minute hand, right now it's a little too long. So we're gonna bring the primary outer edge here back to the edge of this index so that it's not obscuring that index at all. And then I'll probably shorten this tip to go right to the center here. Because regardless of what time it is, particularly at night, we don't want any of the hands to fully obscure one of these indexes. So on the hour hand, same is true. We don't want the end of the hand here to obscure any of the numbers, the numerals that we have on the dial. So that's why I have it cut to that length. And then on the second hand, we want it to come kind of almost to this element, but not quite. It's nice to have a little gap. Particularly with the color. So you have this nice black space between the white line and the color of the second hand. That sort of just helps to really define each element. And then you can see on the second hand, we have this huge counterbalance back here. Now on this hand, it'll actually be the counterbalance that's carrying the loom. And that's to help balance out the length of this, the front end of the second hand, because we carefully calculate the mass, balance, and inertia of our second hands to help maintain accuracy despite shock. So when a watch is impacted, if this second hand is out of balance, the second hand can actually either skip a step or it can actually move. Depending depending on how strong the shock is, but maintaining a perfect balance ensures that that shock isn't loading one end of the hand or the other, so it'll actually maintain its timekeeping. And that's particularly important in motorsports like off-road racing. We do watches for trophy truck drivers or motorcycle drivers because they're constant vibration and constant impact of the watch against the frame of the car, the roll cage, on the handlebars of the motorcycle, it's vibrating and so on. So we really want to maintain that balance. It's less critical here just because of the way the gear ratios work. There's a lot of mechanical advantage inside of the gear train, particularly in the hour hand. Some of our minute hand designs do actually have a counterbalance. The new Mark II has a counterbalanced minute hand as well. Another consideration for us is going to be overlaps and near overlaps. So we want to look at the handset as a whole and see how the shapes interact with each other when the hands are either perfectly stacked or when they're nearing an overlap like this, to make sure that you can differentiate each hand until they're almost fully overlapped. And even when they are, there's still enough of the hour hand, for example, sticking out on the sides that you can differentiate those shapes. And that's something that can help a lot with visual acuity. We want your eye to acquire the position of these hands as quickly as possible and be able to distinguish those shapes from one another. And that's what helps with legibility of a display, so that you can read the time super quickly under various lighting conditions. So one thing we might do, looking here, is I might actually extend this tip on the hour hand just to create a really nice, clean differentiation from those tips. And that way when this minute hand rotates just a little closer, right, and it's overlapping like here, you'll still have that tip sticking out just a little bit farther. So it'll give better acquisition as the hands come closer, whereas now I feel like this gets lost a little bit. So that's something we'll probably work on and extend this tip. So the other thing that I'll work at the same time is a line drawing. And the line drawing is identical to the color rendering, so they get updated together. But the line drawing kind of helps me to see the balance and proportion of the elements to one another more easily than sometimes the color rendering can. And it also helps me to do layouts. And then we'll actually generate, if we're doing plate engraving, we'll actually generate the engraving file from this line drawing. So on this one, you can see these two red circles here are going to be the position of these screws to secure the dial to the module housing, not to the movement, but to the module housing. This is the position of the automatic date window. That's the position of the HAQ window, date window. And then this circle is the outer edge of the view window for the watch case. And then this is case, this is the bezel insert out here. So we kind of want to look at everything together and establish kind of a balance, of how these elements are going to work together. We don't want the bezel to overpower the dial. We don't want the dial to overpower the bezel. And so it's a constant balancing act to create something that's visually balanced, but also easy to read. The reason I call the design process iterative is because it is a constant compromise of form and function. Aesthetics are important, but we also have to balance the function of the watch, particularly because what we make are tool watches. Okay, so let me take you through some of the machining strategies to make a dial blank just like this. So this is a Mark I OmniDiver automatic blank with the date window and the balance jewel window as well. So we have to do this it's two machines, and we have multiple ops to do it. So we turn the back side, then we turn the front side, and then it has to go into the mill to form all the holes that you see. And the holes around the outside edge are for applied indices. Some of them are view windows. Obviously, the hole in the center is so that we can mount the hands. This is the D42 dial blank. This counterbore area you see in the center here, this is actually relieved to create more space underneath the hour hand. It just makes it easier to mount the hands for us, gives us a little more flexibility in terms of hand spacing as well. But because that's such a thin form, from that surface to this surface here, it's about 9/1000ths of an inch, so like 3 sheets of paper stacked together. We have to support the full span of this surface when we turn this counterbore, because if we don't, being such a thin form, it'll actually flex underneath the cutter pressure, and instead of cutting the material, it'll kind of just sort of flex it, right? It'll bend it back, and you either end up with a curved surface that's thicker in the center and thinner on the outside edge, or you actually end up with like a bowl. So what you see back here, this is actually a support fixture, so it's not for work holding, it's just for surface support for this thin structure. So op 1 on the dial is going to be same thing. We're going to have a facing operation, so we're going to come in, clean off that face. This is actually, we're starting with the back side of the dial with this huge counterbore. The next step is to rough turn the OD of the part. We're going to come in, finish the OD, going to drill a center hole here. Then we're going to start roughing out this counterbore. And at this point, you know, this part is unitary with the rod, so there's tons of support here, no issues with flex, so we're going to come in and be pretty aggressive, just rough that out. And then this finish pass is going to put a really nice smooth finish on here, and it's also going to add this small chamfer on the part as well. Last op is a parting op, so we'll come in with an ISCAR 120 thou wide parting tool, and we're just going to come right down to the center and part this off. Turning it over now, we're going to start working on the front side of the part, and the front side is obviously more critical in terms of surface finish because that's the part that you're going to see, you know, as the actual dial. Now we're going to put it in work holding so that this surface is interfacing that surface, so that the full width of this thin section is fully supported in the lathe. First operation, same thing. It's going to be a facing operation. Usually I'll leave about 5 thou of material just so I have something to kind of come in and clean up there. Then I'm going to come in and rough out the counterbore, same as on the back side, and then a profile finish on just this counterbore face, and it's also going to, again, it's going to put a decorative chamfer in here as well, right there. So that's 45-degree chamfer. Okay, so once I have all the tool paths finalized, and they're all represented here by these different lines and colors and so on, we're going to post-process that to generate the G-code. So the G-code looks like this. This is the actual G-code that we're going to use, and that is the computer code that's telling the CNC machine exactly what to do. So it's telling the axis drives how far to move, how fast to move. It's also telling the turret which tool to select as it's cutting the material. All right, guys, so we're over at the CNC lathe now. I just realized I'm not wearing my safety glasses. How do you do that? Boom. Okay, so we're gonna take some 1.5-inch material like this. I already have it loaded into the lathe here. It's in the chuck, gonna use a 3-jaw chuck for this. Obviously all of our smaller work we do in collets, bigger work we do in chucks. So what I have is a setup sheet that shows me all the tools that we're going to need to use. So it allows me to check the machine and make sure that the tools are actually in there and that they're set up correctly for this particular program. There's a thumb drive that has the actual code on it, so we'll upload that into the computer. And then I also have an inspection print. All right, so the tools for this one, I put the gang block back in the lathe because we need to do some hole drilling. I tend to keep the drills in the gang block just because I change those out often, and it's just super easy. You know, because these centers are all located in the computer, so all I have to do is set the Z offset, and I already know where all the centers are. So really convenient and much faster to spot, drill, and countersink if we need to do, you know, all 3 ops on a hole. So the other tools that we're going to use for the first op is back to the trigon for the OD turn and face. We've got a solid carbide boring bar. That's our cutoff blade. This is a 5/8 inch diameter flat front carbide insert drill, and then we have our 55-degree diamond in the back as well. You can see that big chip coming off. So it's basically cutting a 120 thousandths wide groove all the way to the center of the part. And because we're running constant surface speed, you can hear the lathe speed spinning up. And that maintains the surface speed. As the diameter decreases, it increases the RPM of the spindle to maintain a constant surface speed of the edge, the face of that material as it's passing by the cutting edge. Well, it's cutting off. This is always the most nerve-wracking part because you never really know exactly what you're gonna get. But at least at this point, you know that, there it goes, that's the part. Let's see what we got. Okay, so here we go. Here's our part. All right, guys, so this is the part that I just pulled out of the lathe. We're gonna do a full inspection on this, or at least on our 4 critical dimensions. So on my print, I've identified the 4 things that I need to check to make sure that this part is compliant. So we're gonna go ahead and do that. Now, those of you who are familiar with this process are probably saying, hey, where's the CMM? Well, we don't have one. So we're gonna do it old school. We do an optical comparator, but for this super simple inspection, we can do it with just these few old school metrology tools. Taking a look at the surface finish, I don't know how well you guys can see that, but we have a really nice surface finish. It's extremely smooth. Let's check our part thickness. So the nominal thickness is supposed to be 50 thou. I programmed it to leave an extra 5 thou on it when it did the cutoff. So you can see what we have is 55.5 thou, so that's perfect. Now we're gonna check the outside diameter. The nominal off of my print is 1.276. We've got 1.276 and 4/10, and our nominal is 1.276, so we're right on the money as far as OD on this part now. Third thing we're gonna check is the center hole. My nominal size on that is 78 thou. Actually, it's 78 and 1/10. So I just have 2 pins here. I'm gonna use them as a go-no gauge. So first thing I'm gonna check is a no-go, and that's the 79. And then if the hole is, it should pass the 78, and it does. So the 78 goes in, the 79 does not go in. So that's a good hole size for our center hole. And the other thing we need to check is the bore diameter before that was large. We know that this is 1.0082. So I'm just gonna put, it's a little tight. I mean, it's basically a line-to-line fit. It's supposed to be 1.009, so 1 9 thou. So I'm just gonna add another half a thou to that offset, and then these parts should be good to go. And the last thing I need to check is the depth of the counter bore relative to the upper face here. So I'm gonna set up a simple drop indicator. I'm gonna zero it out on that lower face, and then we're simply gonna drop the indicator tip here, and I'm at 30.5. The nominal dimension's 32, so I can go just a little bit deeper, and again, that might just be an offset issue. So I'll change the Z offset on the small boring bar by 1/1000 of an inch, and that should give us exactly what we need. So 24 D42 auto dials and some finishing fixtures down there in the bottom row as well. So now I'm getting the lathe configured to do 24 D42 HAQ dials, because we are doing D42 as either HAQ or auto, just like we do with OmniDiver. Okay, so now that we have the backs of the D42 autos done, you can see this is one of them here. We're gonna move on to the D42 HAQ, and I'm actually gonna machine these the other way. So I'm gonna machine the front first, and what I wanna show you guys, see how there's a deep pocket in the back of this auto dial that we've already machined? Well, the HAQ is actually the other way. So the deeper pocket is in the front. This is actually the front of the dial here. And you can see if we look at the back, you can see it's really shallow. So it's 0.008 of an inch deep. And when we're machining stuff, we really want to make sure we're doing the bulk of the machining when the part is still in solid rod form, because there's just a lot more to grab onto, right? You know, if I have this in the chuck, I have a ton of material that I can grab onto. So we want to do all of this bulk machining, you know, in this case, the front, when we have a lot to hold on to, because that's going to generate the most amount of force, right? When we're doing this big pocketing. Then we're going to part it off. And once it's in this form, after it's been parted, there is so little to grab onto that we want to do the least amount of machining possible, because the cutting force is generated can actually, you know, if the cutting force exceeds the clamping pressure, it'll pull the part right out of, you know, the work holding solution, whatever you have. And then you've got parts flying around the lathe, and that sucks. So for this one, we're gonna start on the front, and kind of the same thing. First thing we're gonna do is a facing operation, and then we're gonna do a rough OD turn. Then we're gonna do a finish OD turn. Then we're gonna drill in the center of the dial to mount hands. Next thing we're gonna do is go in with that 5/8 inch flat insert drill, and we're just gonna remove as much material as we can, and that gives us a good starting point to rough out this counterbore and then this additional recessed area here with our small solid carbide boring bar. We're going to do 2 finish passes to give this a really nice clean surface finish, and then same as the other one, we'll part it off here, leaving about 5/1000ths of an inch on the back side here. Just finished writing the first article, and it's always a little bit like Christmas because you never really know exactly what you're going to get. So it's always like, did I program it right or didn't I? Let's find out. Okay, let's see what we got. Where is it? There it is. Well, it looks good, but of course we don't know until we inspect it. So let's do it. All right, so the first thing I'm going to check is the hour hand recess. It's about 14 and a half thou. It should be 15, so that's a half a thou off. That's within our tolerance. So then from this surface, we're going to zero it again. We're going to go to this outer face here. That's supposed to be 30, and it is 29 and a half thou. So again, off by half a thou, and that's well within our tolerance, so that part looks really good. Last thing I want to take a look at, surface finish looks really good. We know that our depths are good, the OD is good. We haven't formed the back pocket yet, so we don't have to check that. So I know that we used the right drill. We used a 62 and a half thou drill. You can see the hole here all the way through the part, right? So I think what happened when it did the finishing pass with the boring bar, it works from outside to inside, and I think it actually pushed a chip as opposed to cutting. It pushed a chip across that center hole. So we could either punch that out by hand, or I can just change the program to go back in right before it cuts the part off, to go back in with that same drill and just drill out that center hole to remove that chip. So I think that's what I'll do, because it really only adds about 10 seconds to the program, and then the part comes out of the machine perfect, and we don't have to do any hand rework to that center hole. Obviously, 95% of our time goes into actually making watches, not videos, so there are parts of this video that I'm sure could be a lot better. I hope you like it. Definitely comment below if you have any suggestions on how to make part 2 of this series any better, or if you have ideas for other videos, we'd love to hear them. Smash that subscribe button if you like the videos we're making. Definitely gives us motivation to keep making videos.